Did you know that physicists can sometimes act like fortune tellers? And no, we're not talking about astrology. Forget all that.
If you want to know exactly where you'll be 5 years from now, ask a physicist, specifically a quantum physicist. They can tell you with extraordinary precision. But they'll need some information about you first, some fundamental information. They need to know exactly where you are right now and your current state.
And no, we're not talking about your financial status, your psychology, or your education. Physics doesn't care about any of that. We're talking about your quantum state.
Once a physicist knows your quantum state, they can tell you exactly when and where you'll be. No magic involved, just the straightforward application of some elegant formulas. Now you might be thinking, wait, isn't quantum physics all about uncertainty, where nothing is definite and everything is just probability? You're right, that part hasn't changed. But here's the thing, just like in classical physics, quantum physics has its own form of determinism. Yes, we might not know exactly where a particle is, but we can describe the probability cloud it lives in. We know where it could be. And as time passes, that probability cloud moves and evolves, but we can predict exactly where it will be. What we're really talking about here is a fundamental truth of physics. If you know the quantum state of an object, a system, or even the entire universe, the position, momentum, spin, and every other property of every single particle, you can determine not just the future, but the past as well. Exactly. This is the foundation that all of physics rests upon. Without it, the entire system collapses. Without it, we can know nothing. But in everything I've just told you, there's one crucial element hiding in plain sight. Information. Yes, information. This is the foundation we've been talking about. Information cannot be created from nothing, and once it exists, it cannot be destroyed. Information always has been and always will be. Information in the universe never disappears. It will never disappear. It cannot disappear. Because if it did, as we said, the entire system would be in grave danger. And the world of physics has crashed headfirst into an incredible obstacle on exactly this issue: the black hole information paradox.
But first, let's clarify exactly what we mean by information. Let's talk about the law of conservation of information. Conservation laws are absolutely fundamental to physics, and really to all of science. Take the law of conservation of energy, for example. In a closed system, energy must remain constant. As long as it doesn't interact with anything outside, the total amount of energy stays the same. It only transforms form. Transformation is possible, but destruction is not. And when we think of the entire universe as one closed system, the energy inside it is constant and unchangeable. Now, when we apply this same principle to information, to the conservation of information, things can get a little confusing, because in our everyday lives, we create information all the time, and we destroy it just as easily. But in the quantum universe, information can neither be created nor destroyed. When you think you're creating new information, you're actually just rearranging existing information into a new form. With this logic, whether a particle is sitting in an empty box, caught in a complex chemical reaction, or part of the entire universe itself, if we know the system's position, momentum, spin, electric charge, and every other property, its complete state, we can predict exactly how it behaved in the past and how it will behave in the future. Let's push the boundaries a bit to really understand this concept of information. Imagine you're holding a book. In physics, they usually use a dictionary as the example. So picture a thick, heavy dictionary in your hands. Now you burn that dictionary. It turns to ash. All you have left is a pile of gray cinders. Every word that was in it, every definition, every cross-reference, every example. What happened to all that information? Gone, right? Nope, not gone, not even close. All the information from that book is still there, inside the ashes. Sure, extracting it would be incredibly difficult, but it's all still there. It hasn't gone anywhere. In theory, if you could collect every single atom produced by the burning and arrange them back in the right order, you could reconstruct that dictionary from scratch. So, information at its most fundamental level is simply different arrangements of particles. That's it. That's all it is. As we discussed in a previous video, quarks and electrons arranged one way become a rock. Arrange those exact same building blocks differently, and you get a deer. Same material, different information. A rock and a deer. That's what information really means. Now, as we discussed when talking about black holes, from an outside observer's perspective, nothing actually falls into a black hole. Due to time dilation, we observe objects freezing at the event horizon. Of course, if this were a space shuttle, the story for the people inside would be very different, but that's a tale for another time. Because the point we need to address when we're talking about why conservation of information matters so much is this. What happens to the information of an object that falls into a black hole? Well, when we're dealing with near infinite gravitational force, which we know we are, there's actually no problem at first. The information of an object falling into a black hole, from the perspective of someone inside the spacecraft, falls all the way to the gravitational center and stays there. For an outside observer, it sticks to the event horizon and stays there. From that perspective, there's no problem. The information is still there. It's not being destroyed. We just can't access it. That's all. But then, Stephen Hawking enters the picture. No scientific discovery can be attributed to just one person, and this story is no exception. In 1973, when Stephen Hawking was in Moscow, Soviet scientists Yakov Zeldovich and Alexei Starobensky told him something remarkable, that rotating black holes create particles and essentially spray them out into space. When Hawking took this insight and ran the calculations himself, he discovered something even more extraordinary. Not just rotating black holes, but all black holes, even stationary ones, produce radiation. It meant black holes have a temperature, and through what we now call Hawking radiation, black holes are actually evaporating, like water boiling on a stove, losing their energy and therefore their mass. Black holes, it turns out, aren't actually black at all. And so, eventually, given enough time, a black hole will completely evaporate and simply vanish. Now, it's worth noting that this process takes billions upon billions of years. But the theory stands. The reality stands. Black holes die too. And this is where the real problem, the enormous problem, hits us right in the face. Remember, information cannot be destroyed. What happens to the information belonging to a spaceship that fell into a black hole, to stars, to anything that was consumed? Where does all that information go? And there it is, the black hole information paradox. Here's the crux of the problem. Hawking radiation, call it what you want, is thermal radiation.
It carries no information whatsoever.
It's completely random radiation. And regardless of what's inside, all black holes evaporate with the same kind of emission.
Hawking radiation depends on only three things: the black hole's mass, its spin, and its electric charge. Nothing else. Those are the only properties that matter. That's why all black holes with the same mass, spin, and charge are completely identical. The information about the particles inside, it's nowhere to be found in the Hawking radiation. And with this radiation, this evaporation, the day will come when the black hole dies and the information? Gone. Or maybe not. I know, it sounds like a dead end. Don't worry, the scientific community feels the same way. For nearly 50 years, we haven't been able to fully solve this paradox. Have we given up? Absolutely not. There are several competing theories out there. Let's look at the most prominent possible explanations together, and I want to hear from you in the comments which one you think makes the most sense. Here's the biggest challenge. We've known about black holes for a long time. We predicted their existence based on Einstein's general theory of relativity. They're ultimately just an extreme warping of space-time. But when we try to explain Hawking radiation, we need quantum mechanics. We're essentially trying to build a quantum house on a classical foundation, and the two don't play well together at all.
We know that general relativity and quantum mechanics famously do not get along.
To truly explain Hawking radiation, we need these two revolutionary theories, the best descriptions of the universe we have, to somehow come together.
And for the scientific world, yet another great paradox emerges right here. Before anyone says, who cares whether information is lost in black holes or not, we need to consider what that actually means. Let's say whatever's inside the black hole, everything it swallowed and never returned, doesn't matter anymore. Imagine one day it dies, releases all its energy through Hawking radiation, and all the information inside is simply gone, destroyed, and the law of conservation of information, worthless.
Do you know what that would mean? We would have to throw away every law of physics we know, everything, every single one, and start over from scratch. Information, motion, everything. We'd have to rewrite it all.
We've done it before in history, rewritten the laws from scratch. But we've come so far now. It would be both incredibly frustrating and incredibly liberating. Maybe this is exactly the leap humanity needs to make.
Or maybe information isn't lost after all. Maybe the radiation coming out of the black hole actually does carry information within it.
In that case, the conservation of information would remain intact. But here's the problem. For nearly 50 years, every mathematical approach has been tried, and we still can't quite make this explanation work.
Even Stephen Hawking himself couldn't crack it. Either there's something we're not seeing, something fundamental we're missing, or our mathematics simply isn't sufficient. Once again, we might need to start from scratch.
Or, since we don't have a solid answer, we're free to speculate, aren't we?
So maybe we really are losing information. Maybe our universe is being slowly consumed by black holes, piece by piece.
And all that information, everything taken from us, is being sent somewhere else, to another universe, black holes as cosmic tunnels, or perhaps to another time entirely. Or, well, from here on, it's up to your imagination. What happens to the information? where does it go? What happens inside, near, or anywhere around these extraordinary objects is something utterly unlike anything we're familiar with.
And as I said, the more we continue to study black holes, who knows what incredible things we'll discover next.
And in that process, we may need an entirely new physics. For that, we desperately need new Einsteins, new Newtons, new Hawkings. Why shouldn't one of us, maybe someone watching right now, join those legendary names? Why not you?
And as always, until we meet again, I'm so glad you're here. Sending you all my love.